right. So this is a series of lecture for basic topology course. If you're fresh out of high school or a very beginner undergraduate student, or even someone more advanced but who wants to revisit their basics of topology, this course would be for you. The topic for today's lecture is quotient topology. This lecture is supposed to serve as a very elementary introduction of quotient topology, why we define this structure, what's the motivation behind it, and a very intuitive understanding of it with some rigorous mathematical definitions and terminologies towards the end, right? So our focus is first to develop an intuitive understanding, and then we move on to the actual mathematics part of it, right? So this is just a brief outline. First, we look at the intuitive definition, then we look at an example to help us ground that motivation into something more concrete, and then we look at the rigorous definition. And before I start the lecture, if there are any questions, I see some student has joined us. If there are any if there are any questions that you want to ask in between the lecture, feel free to do it. Hopefully it will not be too disruptive, right? Okay. Before we begin, I would like to mention that this book, Topology for Beginners, is a good resource for anyone wanting to study topology at an elementary level. It's a very beginner-friendly book with easy to understand terminologies, exercises, and definitions. So give it a go if you like. All right, now let's begin with topology. Now, before jumping onto quotient topology, it is important for us to recall that the basic idea behind studying topology is to make sure that topology kind of equips you with the tools that enables you to define a structure, a mathematical structure on any kind of an abstract space, right? What do I mean by here? If you recall from your high school mathematics, we study Euclidean space a lot, right? The XY plane, you have a two-dimensional plane, and then you define some sort of coordinate system on it so that each point has an address, and then you can find connections between the points, distances between them. You can draw graphs on them and solve simultaneous equations on them and whatnot, right? So what the purpose of this structure, of this XY coordinate structure on a 2D plane is to ensure that when you have a space, you can do some mathematics on it, right? If you don't have any structure on it, if it's just a 2D plane, right, then it's very difficult for you to study that space in any rigorous fashion. But if you define a structure on it based on some notion of distance or closeness, then you can do a lot of mathematics on it, as you must have done during your high school courses, right? What topology does is it generalizes this notion to more abstract spaces, right? So, for example, forget your Euclidean space, and if you, for example, have a very irregular sort of a blobby space in maybe higher dimensions, so not in 2D, but maybe 4D, 5D, something that you may not even be able to accurately picture or visualize using your tools, right? But if you use mathematics to define a topological structure on it, then you can do essentially the same kind of mathematics on it as you can do on a Euclidean space, right? With functions, with distances, with similarities between points and structures and all of that, right? Now, with this background in mind, I will introduce what quotient topology is. So the role of quotient topology is if you already have some topological space X, right? The role of a quotient topology is is to refine or modify an existing topological structure so that you can simplify your calculations, right? Go back to this example of your blobby structure, right? There's for example, it's a 5-dimensional space with a lot of different points and a lot of complicated structure, right? You want to do some mathematics on it, but of course, if it's a higher dimensional space, there are more coordinates, more equations, more complications. And to avoid that, what you want to do is you want to say, okay, let me just focus on one particular property of this space and then do mathematics on it. That's where quotient topology comes in. It helps you sort of simplify the structure on this space so that you can simplify your calculations, right? All of this will become more concrete as we progress into the lecture, but for now, for the basic motivation, you need to remember that any topological space where you want to simplify the structure, identify points together so that your calculations are easier, quotient topology is what you use. All right. Any questions so far? No? Okay. Let me make this now definition of simplification more concrete. So imagine you have this random space X, right? Now here you have any topological structure. So I'm keeping this quite abstract, right? So no numbers or anything, but for example, you have some points here, some points there. And this is your topological space X with some topology on it, right? Let's call it tau. This is your topological space. Now, you want to study this space, but it's too complicated for you to study it in its current state. You say, okay, for the purposes of my calculations, the only thing relevant to me is the color of the points. So I don't care what the size of the point is or how many there are. I just want to know, for example, if a point is a particular color. Okay? So what you do is you take the same space. Maybe I could just copy it instead. So this is your same space X, but now instead of having all of these many different points, what you're doing is you're saying, okay, I'm going to club all of the orange points together and just have one class representing the orange points, and then club all the pink ones and have one class represent all the pink points, and then similarly just one class representing the black points, right? Now this new space, so this is no longer just the space X, you can call it a new name. This new space, here you can see now you only have 3 points. So of course it makes sense that the mathematics would become easier for you to do some calculations on it. The structure is simplified. You don't need to worry about maybe the dimensions is even reduced, you know. So this process of identifying one particular class of points together and the other class together and the other class together, this is basically this simplification process is what a quotient topology does. Now, of course, there is a lot of mathematics behind. So for example, how do I do this simplification? You know, what makes it mathematically accurate for me to just take all of these 5 or 6 points and represent them using just one point, right? Of course, there's mathematics behind it, the rule for simplification, right? So the rules for simplification, that's where the actual topological notions come in. But for the purpose of this slide, you need to remember that this is what essentially a topological, a quotient operation is doing, right? A simple example of it is, for example, I'm explaining the process of factoring out, right? So I'm having pizza with my friends, and there are 12 slices in the pizza, and I say I ate 3 out of those 12 slices, right? It's easier for you to understand if I say, for example, I ate 1/4 of the pizza. So essentially saying that 3/12 is the same as 1/4, or some other large fraction is equal to some smaller, simplified, reduced version of that fraction. So you're basically factoring out all the commonalities and all the redundancies from this structure and presenting it in a very simplified manner. That's basically what we're doing, right? That's the point of quotient. Now, so this new space here, this would be your quotient space, and you define a new topology on it. We will see later how do you define that topology. One example of it is a torus. So a torus is a very famous topological space, one of the very basic spaces that you study in topology. And a torus is like a hollow donut. So imagine a donut, but with no fillings inside, right? The outline or the wrapper of a donut. You can see this torus as a quotient space. How? You start, so look at this structure first. You start with a rectangle or a square, right? So something like a sheet of paper, right? You start with this. And what you do is you first identify, you glue together. So remember we identified points here when I was explaining factoring out. So you identify the two edges, the left and the right edges, right? You say this is basically one. So identifying them means you sort of glue them together, forming a sort of a cylinder. This left and right, glue them together, you form a cylinder. And then in the next step, this top and bottom edge. So now your top edge looks like a circle because you identified the left and the right, and the bottom edge also looks like a circle. And then you identify these two circles together. So with my sheet of paper, and you can easily verify this using any sheet of paper that's lying around. So this is the cylinder that we have, and then this end and this end. These two ends, if you sort of glue them together, you will get the shape of a torus. Right? And now you may be wondering, okay, we did this, but why do we need to do this? Why do we need to define a quotient topology on a square, right? One very basic example of it is this video game. So this is from before the smartphone era. This used to be a very simple video game on a Nokia phone if you ever used one. The concept of this game was that you start out, there's a snake, and that snake moves around. You can control the movement of the snake with your cursors. And that snake moves around, and there's some food for it, and the more food it eats, the bigger the snake gets. Now, as long as the length of the snake is smaller than the length of your screen, you have no problems, right? The snake can freely move around. But for example, you eat too much food, and now your snake is like this long, and it can't fit on the screen. What that game did was that if your snake exits the screen from this side, it would automatically enter from the other side, as you can see here, right? So the snake entered, the tail of the snake is here, and the head is here, and it entered this, exited the screen from the left, and then entered it from the right. Right? Similarly, if you, for example, this snake exited it from the top, it would enter from the bottom. And this is essentially saying that the snake lived on a torus instead of a, you could see it on a rectangular surface, but it was actually living on a torus. Because if you're in a rectangular room and you exit, so the right edge and the left edge is the same, right? So If you are touching the right edge, it's the same as touching the left edge, because remember, we identify these 2 points together. So that means that if you're entering this, exiting the screen from the right, or you're touching the screen on the right, it's the same as touching the screen on the left. It's like if I'm in my room and if my room is actually a torus instead of a rectangle, if I leave my room from the behind, I automatically re-enter my room from the front, instead of just entering into another room. So whoever was designing this game, they wanted to project the movement of the snake onto a rectangular flat surface, but the snake was actually operating as if it was inside a torus, right? So if you want to, the point of where quotient topology helps us is that if you want to study the movement of the snake on a torus structure, but you do not have the capacity to visualize a torus, you could very easily just do all of your calculations on a rectangle with this additional structure, that the left and the right edge of the rectangle and the top and the bottom edge of the rectangle are the same, right? So this is just one example of how defining a quotient structure on one topological space. So this is your topological space X. You define a topological structure on it, and now you've converted into a different topological space and a more simpler way of studying the space. You've developed a more simple way of studying the space, and now you can do all of your calculations on this using this simplified structure. Is it clear so far? Does it make sense?
Yes, it's clear.
Okay, good. Now that we have this intuitive understanding of what a quotient operation does to a topological structure, we move on to the actual mathematical definition of it. In order to understand a quotient topology, you need a set of 3 definitions. So first you define what a quotient space is, right? Now, you start your definition with a regular topological space. So X is any topological space. And what you do is you define an equivalence relation on it. Now, equivalence relation is a mathematical term. If you're not aware of it, it's just simply a relation, any kind of way to relate two elements, which is reflexive, symmetric, and transitive, right? You can look this up if you're not already aware of it. The main idea behind an equivalence relation is that if you have a space and you have many different points inside of it, you find some way of identifying them, right? So if we recall this structure, here, I should paste it. If you recall this structure, here we started with our topological space X, right? This is your topological space X, and now you want to simplify it by identifying, for example, the orange color points together and the pink color and the black color together. So this process of identifying, behind this process of identification is this equivalence relation. Right? So for this particular example, any point X, let's call this X1 and X2. Right? So X1 is similar to X2 or equal to X2 if and only if they're orange, right? They're the same color. The same color, right? based on this equivalence relation, if you apply this equivalence relation to your space X, this is what you will get, right? So a quotient space is basically, you start with a topological space X, you define an equivalence relation on it, and then you use that equivalence relation to get a new space where the members of this new space are all the equivalence classes of your elements here. So what do I mean by equivalence class? If x1 is the same as x2 and x3 and x4, right? I can use just one element, for example, x bar, to represent all of these orange points. So this x bar is the equivalence class of all the 1, 2, 5, 6 orange points in this space X, right? So the quotient space Y is the set of all equivalence classes of your elements in the original space, right? And you use this as a standard notation for it, X over like a division or a factoring out of it based on this equivalence relation, right? Now it's important for you to remember here that on the same space, so on the same space X, you can define a different quotient structure if your equivalence relation becomes different. So now, for example, I say x1 is similar to x2 if and only if they're the same size. Or for example, if they are the same distance from the origin. So this is the origin, and if they're the same distance, right? Then the quotient space that you have, it will not look like 3 different colored points here. It will look different because now maybe you have all the orange points of one particular size, and then of another particular size, and another particular size, and then all the pink ones of one particular size. And maybe different colors also have different sizes, right? So for example, there are one orange and one pink is the same size, right? So then you no longer can use color to represent your equivalence classes. Then you maybe use some, for example, XA, where A is the size. So XA represents all the points of size A. For example, A is equal to 5. So X5 represents all the points of size 5, right? Diameter 5 maybe. So the point of this example is that your original space is the same, X is the same. But if you change your equivalence relation, then the resulting quotient space, the resulting simplified space will look different, because then the equivalence classes become different. The rule on which you're factoring out your information, the rule on which, based on which you are identifying your points, is if that becomes different, then of course the resulting space becomes different, right? So let me just read this definition once more so that the idea is reinforced. So a quotient space, let X be a topological space and tilde be an equivalence relation on it. Then the space Y, where X, which represent as X over tilde, containing all the equivalence classes of X, is called the quotient space of X under the given equivalence relationship. Now, in order to represent your equivalence relation better, we most of the times use a quotient map. So a quotient map is basically a map from your original space into your quotient space. It has to be a surjective map that maps each element X to its equivalence class in Y, right? So yeah. I'm going to erase this part and stick to our original example here. Okay, so for example, here, this one's X1, X2, X3. And let's call this point purple ones y1, y2, y3, y4. And then the black ones are z1, z2, z3, right? So if I want to define a map between the two spaces x and y, what my map f would do is it would take each element of x and map it to the equivalence class. So x1 would be mapped to x bar. And now let's call this class, purple class, as y bar. And then y1 would be mapped to y bar. Similarly, x2 would also be mapped to x bar. x3 would be mapped to x bar. y2 would be mapped to x bar, and so on. Similarly, if this is your z bar, then z1 would be mapped to z bar, z2 would be mapped to z bar, and so on, right? So any map, any surjective map that maps points to their equivalence classes is called a quotient. And this map becomes very useful when you want to define a topology on your resulting structure, right? So recall, so far you have one original topological space X within existing topology on it, tau. Now you have a new quotient space, but you don't yet have a topology, right? You don't know what the open sets look like. And in order to define a topology on it, you need this quotient map. So how do you define a topology on a quotient space? Any set, you take any set V in Y, and you say that this set is open in Y if the pre-image of that set is open in X, right? So, for example, I have this open set that contains X bar and Y bar. This is sorry, not an open set. This is just a set. I need to check its openness. So this is my set V, this pink highlight. Now, is V open in this topology or not? How do we check? How do we define it? We check the pre-image of V under our map S, and we say, okay, the pre-image of V would be all the elements that map to X and Y, which means all of these X's and all of these Y's. Right, so this is now your, maybe I should use a different color for X. So the pre-image of all the X bars, if you remember all the orange points, and the pre-image of all the Y of Y bar are all these purple points, right? So this yellow shaded region is now the pre-image of the set V. And we say if this V, if F inverse is open in tau, if F of V is open in your topology on X, then and only then V can be said to be open in your topology on Y. Right? This is how you define. So the definition of the quotient topology depends entirely on the pre-images under your quotient. Right? Is that clear?
Yes, it's very much clear.
Okay, good. Just one last slide and then we would be done. We can use the same rigorous definition to understand our torus, right? We said that we would define a torus as a quotient space based on this identification, but now we can mathematically actually define the gluing together, right? And how we do it is, so this rectangular sheet of paper that you start with, right? You define it as I cross I, and I is nothing but the unit interval in R, right? Just the interval from 0 to 1, closed interval, right? If you define a product of I with I, basically attaching I many copies. So this interval 0 to 1, and then you have this interval 0 to 1, and then you attach all of these copies together, you will get this rectangle, right? In order to get this torus structure, we need to define this equivalence relation and then a quotient space, right? So consider this equivalence relation. So any element, any point here, for example, x comma y, right? So x comes from I and y comes from I. This is how the points on your rectangular sheet look like. They look like these ordered pairs where, for example, if x is 0.5, then you're halfway here, and y is 0.5, then you're halfway here, and somewhere in the middle is your 0.5, right? So in order to define some equivalence relation where this edge would be identified with this edge, what you say is x comma maybe 0 comma y. So 0 comma y is all of the points on this edge. It's the same as 1 comma y. So y could be anything, right? Any point here, 0.25, 0.5, anything. And then this results in this identification where the first identification where you had this cylinder, right? And then if you say x comma 0 is the same as y comma 0. So x comma 0 is all of the points with y coordinate 0, and y comma 0 is x comma 1. Sorry, that was my mistake. X comma 1 is all of the points with y coordinate 1. If you identify them, then that's the second gluing together of both of these circles, right? This circle and this circle. And both of this combined gives you the equivalence relation that you need to get. So if this is your equivalence relation tilde, and you I cross I, if you factor out it, you will get a torus, right? And then if you want to define a topology on the torus, what you do is you pick a set here, for example, any set, and then you check its preimage. If its preimage is open under this product topology, then the set here would be open and vice versa, right? So that's it for this lecture, this basic introduction of quotient topology. If you have any questions, please feel free to ask them, even if it's a very basic question. This can get very abstract, the notion of constructing new topological spaces from old ones. So if you have even a very basic question, please feel free to ask.
Yes, Sidra, would you like to ask a question?
Or even just a clarification, anything.
Right, so it was a wonderful lecture, and thank you very much for not only the lecture, but also referring to our book in the beginning. And so I just have one, like you said, so it's just a naive question. I've always wondered, like, the idea of quotient space, and it appears like also in linear algebra and in many places. And we also have the idea of quotient groups. So, and it's the same idea essentially. uh so so after after factoring out, and after going from square to torus, so like the number of points would also get reduced, like, so it's a naive question, like square would have more points and torus would have less points.
Yeah, so
And
that's
I
a good
mean,
question.
would it get as big an issue, like if one space is uncountable, and you go and you can transform it to a countable space? So
Yeah,
just comment on that.
Sure. That's a good question. As far as the number of points is concerned, so of course, when you are identifying the whole point of defining a quotient structure, doing a quotient operation, is to get rid of the redundancies and only focus on the property that you want to focus. So in that process, of course, you're intentionally losing information so that you can only focus on the information that you want, right? For example, in this quotient example, before doing the quotient operation, all of these points on this edge and all of these points on this edge, they were considered to be different points. So they were separate points. But after doing the quotient operation, all of these points were identified or clubbed into one class, and all of these points were clubbed into one class. So if you're just looking at the cardinality of the set, in cases where you can, define it and that, it is going to reduce. But again, you need to remember that this is not like going from one set in R square to another set in R square or something. The spaces could be very abstract, and the operations could be very abstract. And basically, you're going from points to their equivalence classes, right? So before doing any kind of comparison, you need to remember that the fundamental structure of the objects are different. So here you have points, and here you have their equivalence classes. So even though all of this is sort of represented using just one point, and you are deliberately obscuring the information here, you can always retrieve that information back if you look at the quotient map that you. Right. So does that make it clear? And as far as countability and other topological properties are concerned, I think I'm not 100% sure about which properties transfer from the original space to a quotient space, because again, the quotient, when we define a quotient map, the only condition on it was that it has to be a surjective map. So it's not a homeomorphism in any sense, right? Which means that, so topological properties are only preserved under homeomorphisms, right? So, and maybe continuous map. So this map is not even, we're not even asking it to be a continuous map. So there's very few restrictions on it, which means that it will not be very good at translating topological properties from one space to another. So when you say countability, I think you will lose it, because when for example, on the real space, you can define a modulo structure and then represent it using only one or two numbers. So reducing the points to their equivalence classes will definitely affect properties like cardinality, countability, and other topological properties.
Yes, I also think so. Right. So thank you once again, and let's hope we can, continue with this series.
If you have any other feedback on just the pedagogical aspects of it, like if the explanations were clear, the drawings, the pace.
Yes,
The
like I'll share the link with you, and as we discussed, like it will be available on YouTube also. And let's
Mhm.
hope that we get more feedback, you know.
Sure, sure. I would very much appreciate, because of course this is I'm not used to this mode of teaching. So any feedback regarding just the teaching aspects of it, not the content, but just the delivery aspect of it, would also be very much appreciated.
Yes, let's hope that we get feedback on this lecture. Right. So thank you very much, Huma. And I'm so now ending this session.
Okay,
All
good.
right. Take care. Bye.
Bye.